That okay? This is a thinking process. And this thinking process is basically is this. Once we have the over-constraint problem, we target on one constraint and try to release or virtually remove the constraint by this. And then for that removal, in practice, is not possible. So to take care of this virtual replacement is this. We add in a reaction force and to push back the material to the wherever they stop. That be okay? Any questions? And then we can proceed to do the calculations. For this case, let me do the calculation here. So let me call this delta B. And let me call this is a subsystem 1. This is a subsystem 2. For subsystem 1, we can calculate delta B is this. Let me convert it into the vertical one for easy illustration. Okay, so that is the delta B here, and this is P. So the same thing we are going to try is use our techniques. So let me analyze the reaction force in each segment, and then using our techniques we done earlier. Okay. So this is a reaction force. So you can see if we take the cross section here, so that free body diagram, let me draw that here. How about this here? For this problem, the constraint here, if we move it, we take the free body diagrams. And this is the reaction force, here is P. Okay, so that is the free body diagram on this part. And then if we take any cross section in this segment, you can see that section this is the force P here, and by equilibrium this is force P. So that means in the first segment, the magnitude of the reaction should be equal to P, and that's going to stretch. So that is P here. And again, the point upward is to represent the stretching of the section. The downward is representing compression. And in the second segment, again, we take the any section. So here, that is a free body diagram here. And here, this is a P. And in the second segment, if we take any cross section, from here you can see this is a P from at the loading at the constraint here. And to the here, we have nothing. So in the second segment, we don't have anything. Are we good? Okay, so on this case, we can work on the delta B will be equal to PL over EA, our generic formulas. And here we have two segments. For the segment 1, segment 1 plus PL over EA. And for segment 2, in the second segment, P equal to 0, so we don't need to calculate. So for this case, this will be equal to, what is P? P equal to PL over EA. And L, for example, let me call this is the segment is LA, and the second one is called the LB. So here should be LA, right? Are we okay?
for that step, you're combining the system 1 and system 2 equations.
Yes.
Okay.
Yes. Basically, this is what we have done is this.
Wouldn't there be the 2, wouldn't you have, since you're adding 2?
Adding together.
Yeah, so it's 2. Yeah.
Fusing, and this is 0.
Okay, so.
Because here, right?
Yeah, okay.
Okay, and now we have solved the delta B. Yes.
So is the second one P0 because there's an internal force P? Is that what
Yes, because the internal force P equals 0. Here. Right.
You have to imagine if there's a really long rope and you're hanging from the middle of the rope, there's going to be tension on the top of the rope, but there isn't any tension on the bottom of the rope.
Like these, I fix here, apply the loading to say here. Okay, so that means you can see in this red portion is under loading, but the lower portion, our second segment has no loading, right? Can you feel it? That is exactly this situation, like this. Okay, so that is the first case, and now from here we can solve for the problems. Let me erase this one. So now we have solved for B, and now here you can see from our beginning analysis, for the second subsystem, the reaction force is to push back the virtual displacement by the same amount, delta B. So that means for the subsystem 2, for the subsystem 2, the RPL over EA for the subsystem 2, the whole thing is like this. We have the system, let me tilt it into 90 degrees, and this is the reaction force here, RB, which is unknown. For the subsystem, we are trying to, the reaction force is to push back the subsystem 2 by that much. By how much? By delta B. Right? Because we have, in practice, we have sustained the end at the ground here.
That's because the whole deformation
Yes,
is 0.
because the whole definition is
Has
0.
to be 0. Okay.
You are just saying that is the compatibility equation for this question.
Delta B plus delta R is 0.
Yeah. Okay. So for this case, why this delta B is translated to here? Because they have the same amount. That is the compatibility. That is the compatibility equation for this case. Okay. So that means here you can see delta B equal to, for this example, is PL over EA. And again, delta equal to PL over EA. This is our generic template. And for this case, what is the P? P is the force RB. And what is L? So let me call the whole entire length is L basically equal to LA plus LB. Okay. So this is LA plus LB over EA.
Wait, so that includes the deformation?
Including deformation, again, back to our original deformation, we ignore, we just take the original length. In practice, the deformation is very small.
Well, I'm wondering because you used LA and LB earlier.
Yeah, so if you wish, in more accurate expression should be plugged in like this.
Yeah.
But most of the time, I can tell you this calculation, if in terms of number, that is always is in terms of millimeters compared to meters. So this one we can just ignore.
Okay.
In this class, and again, we don't consider such a accurate description. That okay?
Yeah.
Okay. So now this is the PL over EA, this generic. And what is delta B? Delta B is translated from what we have done earlier. So we copy from the information from the previous case. Is PL over A, EA. If you look at this side, the right-hand side and the left-hand side, RB is the only unknown we're looking for, right? So using the Q side, we can solve for RB.
So LB equals 0?
Not equal to 0.
Oh, RB, okay, never mind.
That will be equal to LA plus LB, LA times P. So back to our original problems. If that is a bar, if I apply the loading and say like here, so the top is fixed, bottom is fixed, I try to open this cap, and you can see right now I try to open this cap, supposed to be like this, right? But now the top and bottom has been both fixed. So this portion and this portion, they will be under different direction, right? And the bottom one, the direction is calculated by this one. A bit good? Okay. So once we have RB, then what direction and our idea? So simply we know that the RA plus RB equal to P, that's taking the force equilibrium. Then you can quickly calculate RA. So this is P, and this is reaction force RP we're looking for. The other side is RA. So therefore, RA plus RB by equilibrium equal to R. And that is take the force equilibrium in one direction. So therefore, we can calculate RA equal to, this is P, equal to P minus RB. And that is equal to LA plus LB and LB times P. Okay, so any questions about this process? No, then let me erase this one. And there's a different approach to solving this problem, like this page here. And textbook provides a detailed description about this process, but let me skip out this part because as long as we have one, I think it'll be plenty. And this is to summarize our approach here. And again, one more time. Here, this is the over-constrained problems, and we focus is try to imagine to relax or to move the constraint. And by replacing the removement of such constraint by two things. One is a virtual deformation plus the reaction to push back that one. So what the overall is we have to keep this end at the same ground here. Okay. So that is the thinking process. And translate the displacement from here, from the subsystem 1 to subsystem 2, that information is what we call the compatibility equation for this problem. The next page, I believe, is a more concrete problem statement. We can work on the numbers for this and quickly. For this, again, look at this problem carefully. We have a non-uniform drive and Q loading applied. But again, this is similar to the previous one. They both constrained on the top side, on the both sides. So by all means, before we develop the numbers, we must know the reaction will exist here and top. And the strategy, again, is we try to relax we focus on the bottom one and we remove this one, and then let me work on the board with you carefully for this question. So I like to turn off these slides, and I want to give myself more space. So let me translate the product into the horizontal direction. So that will be this. And here is the loading here, and another loading here. One is 300 kilonewton, and this one is 600 kilonewton. And here we are given the dimensions. Um, 0.15, 0.15, 0.15, and 0.15. That is meters. We have the cross-sectional area for the first one, A equal to 250 millimeter square. For this one, A equal to 400 millimeter square. And for this case, E is
200 GPa.
200 GPa. Okay, so this is ABCD. A, B, C, whatever, D, E. Okay, like this. So again, let me try to repeat the same process. I try to work on this constraint. This is over-constrained problems. So here, the problem will be equivalent to this. Okay, now this is the thinking process. And this is the problem itself before loading. And once this is loaded up by the force here and here, this is 300, this is 600. And if there would have no constraint on this side, and again, right now I'm showing the thinking process. If there would have no such constraint here, then this will free to move at this end to that much. However, the existence of this constraint will actually impose erection force to push back. So for example, on the deformed, the virtual deformed systems, there would exist erection force for the RB. RB will be to push back the deformed, virtually deformed system exactly to where the constraint is. So that means this amount, theta B, must be equal to this amount, theta B. And here, this is our subsystem 1. This is our subsystem 2. Again, translate the equation, the amount here is equal to this one. That is our compatibility equations. We take it from our observation, from our correct engineering observations. Okay, so now we work on the individual systems. So this should be plus. Okay.
Is the convention to use the same delta B? Because it seems like in your notes and in the book, it would be delta R as a reactive.
Yes, either way. Yeah, that is a symbol. So
right. Okay.
yeah.
Maybe it's
So
fine.
basically, whatever the symbol is, we just say this amount equal to this amount. Okay.
Right.
And so now for the system 1, for the subsystem 1. Let me rewrite here again one more time. So this is a loading here, 300, and this is a loading here, 600. And again, I want to calculate deformation delta V.